Friends, myself Ahmad Shafan, and today I am going to teach you chapter number 2. In my last lecture, I explained you about spin quantum number, and in this lecture I am going to start rules for filling of orbitals. So we start from here first. The first rule is Aufbau principle. Students, Aufbau is a German word and its meaning is building up. This principle gives a sequence in which various subshells are filled up, means how the different subshells are filled and in which order they are filled, depending on the relative order of the energies, means electrons are filled in increasing order of their energies. What this principle states? According to this principle, the subshell with minimum energy is filled first, okay, and when this subshell obtain maximum quota of electron or maximum number of electrons, then the next subshell of higher energy starts filling. So it means that the subshell with the lower energy filled first with electrons, okay. After obtaining the maximum number of electrons in it, then the next subshell of higher energy start filling. Here is the sequence of various subshell in increasing order of their energy. The first one is student is the 1s. This is the first subshell. After that, electron goes to second shell. Then after, electron goes to p orbital, p suborbital of second shell. Then electron go to third shell, and in third shell, first electron go to s suborbital or s subshell. Then electron go to p subshell of third shell, okay. After this, electron goes to the fourth shell, okay, in s subshell, okay. After this one, after 4s, electron goes to third shell again in the d subshell. Please remember the order in this manner, okay. In this sequence, 1s is having lowest energy. Then after, electron go to 2s, which is of higher energy, and so on. So electrons are filled in increasing order of the orbitals, okay students. So whenever electron goes to the higher energy level or it is going to higher shell, it means it is filling the higher energy levels. The lower one is having low energy, the higher one have higher energy. So electron is always filled in increasing order of their energies, okay. Now the next principle, Pauli's exclusion principle. According to this principle, no two electrons in an atom can have the same set of all the four quantum numbers. I read again, students. According to this principle, no two electrons in an atom can have the same set of all the four quantum numbers, or we can say only two electrons can be accommodated in the same orbital because their spin quantum number is different, means a maximum of two electrons can occupy one orbital. Third electron can never occupy because the third electron come into the same orbital may have the same spin, and two electrons with the same spin in one orbital is impossible, okay. So in other words, we can say that according to this rule, for any two electrons of an atom, okay, for any two electrons of same atom, A set of maximum 3 quantum numbers can be same. Means 3 quantum number can be same for 2 electrons of the same atom, but the fourth has to be different. Means we can say that the all 4 quantum number cannot be same for 2 electrons of the same atom. If you take 2 electrons from any atom, then the all 4 quantum number for these 2 electrons can never be same. A maximum of 3 quantum number can be same. For example, the electron in the first shell, here 1s1 and 1s2. If I have to write the quantum numbers for this one, the first electron, n is equal to 1 means shell is 1, L is equal to 0, it means subshell is 0, because for S, L is equal to 0, so subshell is 0. M is the magnetic quantum number which depends on the value of L. If L is 0, M is also 0. For first electron, spin quantum number is always plus half. Now if we talk about the second electron, N is same, L is same, M is same, because electron is present in the same shell and same subshell, but this electron will have the opposite spin as compared to the first one. That's why the value of S or spin quantum number will be minus half. Here you can see the maximum 3 quantum numbers can be same, but the fourth one will be different. So this is the Pauli's exclusion principle. No 2 electrons in an atom can have same set of all the 4 quantum numbers. Okay, remember, in an atom, this is very important point. Okay, now the next rule is n plus L rule. Student, the sequence in which various subshells are filled up can also be determined with the help of n plus L value for a given subshell. Means if you can memorize this table, it will be good. If you can't memorize, then you have to take help from n plus L rule. Okay, according to this rule, the subshell with the lowest n plus L value, okay, the subshell with the lowest n plus L value is filled up first. But when 2 or more subshells have the same value of n plus L, then the subshell with the lowest value of n is filled up first. Please memorize this principle. This is a very important principle. For example, as we know already that electron first enter in first S subshell, then goes to 2s, then go to 2s. After this, electron go to 2p, then electron go to 3p, and then 4s. Now if we find the value of n plus L for these, for 1s, value of n is 1 and value of L is 0. The n plus L value for this 1s is 1. Now for 2s, the value of n is 2 and L is 0. The n plus L value is 2. So electron first filled 1s, then after electron go to 2s. We can say that value of n plus L is the order of energy. Means, as we know that electron will go to first that subshell which has lower energy, or in other words we can say electron fill that subshell first which have lower value of n plus L. Okay, so energy is not easy to find, but value of n plus L is very easy to find, and you can find it with the help of this table. Now for the 2p subshell, value of n is 2 and for p, L is 1. Total will be 3. Now this one is important. Okay, now for 3s, the value of n is 3 and value of L is 0. Total will be 3. When 2 subshell have same value of n plus L, then electron will first go to that subshell which has less value of n. As you can see here, when 2 or more subshell have same n plus L value, then the subshell with the lowest value of n is filled up first. So, between these two orbitals 2p and 3s, both have same value of n plus l, but electron will go to first 2p. It is because the value of n is lower. Is it clear, student? Now, next rule is Hund's rule of maximum multiplicity. According to this rule, student, pairing of electron in the orbitals belonging to the same subshell does not take place until each orbital belonging to the subshell has got one electron each, that is, it is centrally occupied. Student, it means, for example, this is, let's say this one is p orbital. Sorry, p subshell. Now there are 3 orbital in the p subshell. If you are going to fill electron in the p subshell, as you know, a maximum of 6 electron can stay. As you know, students, that a maximum of 6 electron can be filled in p subshell. If you are going to fill electron in the orbitals of p subshell, then how you can fill? Students, first electron will go to first orbital, then the second electron will go to second orbital, and the third electron will go to third orbital, then the fourth electron will go to again the first orbital. Okay, so filling of electron in the orbital takes place in this manner. This is called Hund's rule of maximum multiplicity. I read again: pairing of electron in the orbitals belonging to the same subshell. This is the orbitals, one orbital, orbital number 2 and orbital number 3. So these are the orbitals of same subshell. Okay, so pairing of electron in the orbitals belonging to the same subshell does not take place, means we cannot fill electron in this manner. For example, this is p. Okay, if I am going to fill electron in this manner, like first electron I fill like this one, and the second electron if I fill like this one, then this will be against the Hund's rule of maximum multiplicity, means pairing of electron like this one in the orbitals belonging to the same subshell. Here are the 3 orbitals of the same subshell, p subshell. Okay, this pairing does not take place, okay, until each orbital means these 3 orbitals belonging to that subshell, this subshell has got one electron each, means we have to singly occupy the orbitals first. How? Now the second electron will go to next orbital of same subshell. There is one more orbital of the same subshell, so next electron will go to here. Now after unpairing, pairing will start. The fourth electron will go to this fifth here and 6 will be here. So student, if I ask you which one is the fifth electron out of these 6 electrons, so this one is the fifth electron. Okay, so in this manner we fill electron in an subshell. Okay, now next, electronic configuration of atom. What is electronic configuration? The distribution of electrons into orbitals of an atom is called electronic configuration. Just now we have learned about how to fill electron. This is the manner. First we fill 1s, then we fill 2s, then electron go to 2p, then 3s, then 3p, then 4s. This sequence of filling of orbitals in increasing their energy is called electronic configuration. Okay, student. So I move here. What is electronic configuration? Distribution of electron into orbitals of an atom is called electronic configuration. The electronic configuration of different atoms can be represented in 2 ways. Okay, for example, number 1, SPDF notation, and the second one is orbital diagram. Just now I draw one diagram of p subshell, or the 3 orbitals of p subshell. We can write electronic configuration in both manner, in this manner also and in this manner. Okay, for example, if I write the configuration of hydrogen, I can write this in this way: 1s means first shell and subshell is s, and there is only one electron in hydrogen. Or I can represent it in this manner also. S is always, please remember, S subshell is always represented like this because S is having only one orbital. P always represented like this because there are 3 orbitals in P subshell, and D is represented like this because total number of orbital in D subshell is 5. Okay, student. Next, causes of stability of completely filled and half filled subshell. Students, please remember one more thing. As you can see in this diagram, 1, 2, 3, 4, 5. There are 5 orbitals. It means it is D subshell. Which subshell? D subshell. And there are total 5 electrons. Okay. When D subshell have 5 electrons, we say that it is half filled. But if there are 10 electrons, let's say, if there are 10 electrons, means maximum electron, then we say that D is fulfilled. If D have 5 electrons, we say that D is half filled, and if D subshell have 10 electrons, then we say it is completely filled. So our topic is stability of completely filled and half filled subshell. Why these completely filled and half filled subshells are stable? First thing, you must know that half filled and full filled subshells are stable. Okay, or we can say that their electronic configuration is stable. What is the reason of their stability? The completely filled and half filled subshells are stable due to the following reason. Number 1 is distribution of, or we can similar distribution of electrons. The completely filled or half filled subshells, they have symmetrical distribution of electrons in them and are therefore more stable. Okay, students, symmetrical distribution. See, there is a symmetry. There is symmetrically they are distributed in all orbitals. Similarly, in the full filled orbitals, they are also called symmetrically distributed. So the symmetrical distribution provides them greater stability. Okay. Next, the stabilizing effect arises whenever 2 or more electrons with the same spin are present in degenerate orbitals of a subshell. The next reason for the stability is the stabilizing effect arises whenever 2 or more electrons with the same spin are present in degenerate orbital of a subshell. Students, one more thing here I want to tell you that this is D subshell, okay, because there are total 5 orbitals. These 5 orbitals, 1, 2, 3, 4 and 5, they all have same energy. They all have what? Same energy. So if orbitals have same energy, then we call them degenerate orbitals. Okay, so here this word means, just now I gave you example of P subshell. There are 3 orbitals in the P subshell, as you can see, 1, 2 and 3. These 3 orbitals are called degenerate orbitals because these 3 have same energy. Similarly, for D subshell, these 4 orbitals are called degenerate orbitals of D subshell because they have same energy. So stabilizing effect arises whenever two or more electrons with the same spin, these all are in the same spin, we can say their spin is plus half, okay, are same spin, are present in the degenerate orbitals of a subshell. Here you can see all the electrons are having same spin in the degenerate orbitals, that's why they are stable. So these degenerate orbitals electrons, they have tendency to exchange their positions, okay, and during this exchange energy is released. Due to their exchange, the energy is released. This energy due to their exchange is called exchange energy. For example, this first electron can exchange its position with second number electron. Also similarly, it can change its position with third number electron. Also it can exchange its position with the fourth electron. This fourth can move here and one can move here. Similarly, this first electron can exchange its position with the fifth electron. So there are how many exchange? 1, 2, 3 and 4. There are 4 exchanges. So 4 electron by electron number 1. Now here you can see by this this one, the second electron similarly can exchange its position with the third, fourth and fifth electron. Okay, so how many possible exchange here? 3 exchange is possible. Sorry, 3 exchanges are possible here. Now here the third electron can exchange with fourth one and fifth one. There are 2 exchange and the fourth electron can change its position with the fifth one. So total how many exchange? 4 exchange, 2, 3 and 1. Okay, total 10 exchanges are. Greater the number of exchange, okay, greater the energy will be released. See, electron tend to exchange their position. Whenever they do the exchange, energy is released. When energy is released from a system, it got stabilizes. So the energy released is called exchange energy. The number of exchanges that can take place is maximum when the subshell is either half filled or completely filled. So the number of exchanges is maximum when the configuration is half filled or full filled. That's why a lot of amount of exchange energy is released, hence greater will be the stability of such type of orbitals. As a result, exchange energy is maximum in half filled and full filled orbitals, and so is the stability. Students, there are 2 reasons for the stability of completely filled and half filled subshell. The first one is symmetrical distribution and the second one is exchange energy. Greater the number of exchange, greater will be the stability. Now our next topic is shapes of atomic orbitals. Students, here I am going to discuss the shape of various orbitals. The s orbital, first orbital is s orbital. S orbital, students, is spherical in shape. This is the first shell. Okay, this one is the second shell, this one is the first shell. In first shell there is only one subshell, S. In the second shell there is also one S subshell, and inside already there is first shell. So how many S subshell are here? Total 2. This is 1s and this is 2s. So between 1s and 2s there is a empty space, means there is no electron between these space. So this space is called node, okay, or we call it nodal surface. But the intermediate region where probability of finding electron is 0, means here you can't find electron, but in this region you can find electron. In this red region outside also you can find electron. So where you find electron is called orbital, but between these 2 shells, the white region, here you cannot find electron. So this region is called node or nodal surface. Similarly, in 3s, you can see there is 3 red circles and there are 2 red circles. These 2 red circles are nodes. Total number of nodes in any shell is given by n minus 1 nodes. Next, the shape of p orbital. Students, there are 3 orbitals in p subshell. The first one is named as px. This one is called along the x-axis. This is called px orbital. We write like this, okay? S orbital is spherical in shape, students, whereas p orbitals, they are dumbbell shape, okay? P orbitals are, each p orbital consists of 2 sections, better known as lobes. This is one lobe, this is second lobe. Lying on the either side of the plane passing through the nucleus. The 3 p orbitals differ in a way the lobes are oriented. Means 3 orbitals are differently oriented in the space. They are identical in terms of size, shape and energy. Means this one, and this one, 3 orbitals, they have same shape, size and energy. That's why they are also called degenerate orbitals. As the lobe lie along one of the x or y z axis, these 3 orbitals are given the designation 2px, 2py, 2pz, or simply we can say px, py and pz. Similarly, similar to s orbital, size and energy of p orbital increases with the increase in principal quantum number. For example, p subshell of second shell is having lowest energy and p subshell of third shell is having higher energy and p subshell of fourth shell is having even higher energy. So this is the shape of px. Similarly, along with the y-axis, this is py orbital, okay? Similarly, along the z-axis, this orbital is called pz, okay? So there are 3 orbitals. Now the next one is shape of the orbitals. Students, magnetic orbital quantum number or magnetic quantum number gives information about orbitals. So from magnetic quantum number, we know that there are 5 orbitals in the subshell. Okay, these 5 orbitals are designated as dxy, dyz, dxz, dx square y square and dz square. In d orbitals, there are 4 lobes, okay, or we can say they are double dumbbell. P orbitals are dumbbell shaped, whereas d orbitals are double dumbbell with 4 lobes. dz square is like this one, okay? You have to practice, you have to try it 4-5 times, then you will be able to draw these orbitals easily. This is the diagram of dx square y square, means you have to draw the lobes on x-axis and y-axis, okay? Then this will be dx square y square. Now dxy, to draw the structure of dxy orbital, you have to draw x-axis and then y-axis. After that, you have to draw the 4 lobes between these 2 axes, okay? Don't draw these lobes on the axis. If you draw on the axis, this will become this one. This is dx square y square. So you have to draw the 4 lobes between these 2 axes. Similarly, for yz, dyz orbital, you draw y-axis and z-axis and draw the lobes between these 2 axes. Similarly, for zx, you draw one z-axis and one x-axis and draw the 4 lobes in this manner. So these are the shapes of orbitals. S orbital is spherical, okay? P orbital is dumbbell shape having 2 lobes. D orbitals having 4 lobes. okay, or we say double dumbbells. So students, this is the end of this lecture and also of this chapter. You try to solve question by yourself. If you have any problem, you can ask me. Thank you very much. You can see the revised syllabus of this chapter. I have completed all the topics as per this syllabus. So thank you very much again.